Any questions before I start? And our test is Friday. This Friday. Okay. So we have two topics that I'm going to cover. Are we listening to several people? This is cool. 6, 8, 10, 12, 14, 18. You'll listen a few, not a lot. We have array theory and radar in this chapter. We cover the full circuit so you understand that if you transmit a signal and it's received by an antenna, how to calculate the actual voltage on a resistor or power dissipated by those. Y'all with me on that? Now that's important if you understand. I think the next thing I'm going to do is radar, and then I'll do arrays, because it's a natural progression. Now, y'all have heard of radar, right? I teach a course in radar. It's really, radar came into being right about the beginnings of World War II, and that's what was perfected. And the reason is it was used a great deal by the British in identifying enemy aircraft coming over, and so they could set up the Spitfires and intercept the German bombers and fighter bombers. And most of the inventions that actually happen are driven by necessity. They're not by accident. The transistor was by accident, but most are by necessity. Radar was by necessity. Radar is also something, we're going to get the overview, but it's a much more detailed type of topic. And if you're interested, take the course. Radar and sonar are closely related, but it is amazing what goes on. I just want to give you a little perspective, get you interested. Like, what is radar? Well, radar is something where we transmit electromagnetic signals, and from the reflected signals, we figure out distance to target, relative size, and the velocity. Y'all with me on that? That's really what radar is. The acronym is really, it's ranging and detection using, it's really radio signals, but I don't even want to bother with that because there's different things that are said in the internet. Well, let me show you the different types, just in a nutshell. Car radars are something you probably hear about. Some of you probably have radar detectors. Radar detectors differentiate different signal frequencies, K-band, Ka-band, U-band, X-band, all these other things. They don't tell you a lot of information about what type of radar is being used, if it's a Doppler radar, ranging, or anything like that, but it gives you an idea that somebody's painting your car with a signal. Now, that is a type of radar that exposes the sender, and everybody knows that he's sending. That's a dangerous type of radar, because if you are in a combat environment and you expose yourself, somebody can fire a missile, it's a radar homing missile, and blow you up. There's passive radar, where they use signals from all around, and they look at the reflections from those signals and they figure out what's out there. Can anybody think of something that may be akin to that or liking to that? Yeah.
Like when people have radars in their cars, so they can slow down when if a cop's radar on them.
Well, it is a passive thing. But what about your eyes? You don't transmit these signals, do you? But your eyes look at the reflected signals from all these sources, and it triangulates. And because you've got a neural net in your brain that's unbelievable, you've taught yourself that that's a projector, that's a light, that's a door, that's a student. And you yourself can do that just by the photons that hit your eyeball. Y'all with me on that? You can try and, you don't realize what an incredible problem it solves, your brain. Now, passive radars is where they'd like to go, where they don't transmit. And the environmental, the stuff that's in the environment, they just establish they figure out some known sources and they use that. It's an extremely difficult problem, but that's where we're going. All right? I just want to give you at least some idea of why radar is so interesting. Now, you all know that they're delivering packages right now in major cities. I think Amazon's doing it. I don't know if the U.S. Post Office is doing that, using drones, right? One of the biggest problems with autonomous airborne vehicles especially is something that is unexpected. a non-compliant aerial vehicle, frankly, a tree branch, anything. And radar is the way they differentiate where that is usually. Sonar too, but radar primarily. So and they want very lightweight, they want radars that can incorporate a communication signal with the same transmitters. So this is a big, big topic. I'm just trying to give you an idea. If you're looking for something to get interested in, it's on the cusp of really evolving into something that who knows where it's gonna go. Radar, and maybe it won't even be called radar, but radar is sort of it. So now, with that in mind, let's start with radar. So how does radar work in the most basic sense, without going into the depth? What radar is an antenna here. And it can be bistatic or monostatic. In other words, this antenna can be used to send and receive information. Or there can be a second antenna that's used to receive, and this is a transmitting antenna. That's called a bistatic radar. We're going to do monostatic radars for now. It just means the transmitter is the receiver. All right, so this gain of the transmitting antenna will be equal to gain of the receiving antenna. It's the same thing. And the way we start this, we assume there's a certain amount of transmitted power. And this antenna has a certain gain. Then out here, there's going to be a target. Now the target is going to be at a range R. So the first thing we do is find the power density incident on the target from this antenna. And this is the way I tell people to always do this. We're after the power density right here. Y'all follow me? That's so critical. If you can't get power density on a target, you can't get a reflection. So here, and I just call that P incident here on the target. That would be the transmitted power over 4 pi r squared. Y'all realize I always do that. That's isotropic, right? What do I have to multiply this by to get the actual amount, class? No, the gain, right? Or directivity. We'll assume the efficiency is 1, and therefore gain is equal to directivity. Y'all with me? The gain or the directivity sharpens it. It tells you how much better it is than an isotropic antenna. So it's the gain of the transmitter. That's the power density at this target. Now a target is basically identified by one marker, and that is the radar cross-section. So the radar cross-section usually it's termed RCS, or in Dr. Wentworth's book, RCS is identified as sigma. I don't like that, but that's the standard in the industry too. Sigma for radar cross-section. It's in meters squared. Now the radar cross-section of anything is a strong function of the frequency. Let me explain this in a nutshell. If you have a perfectly metal spherical ball and you have an incoming wave on it, at very low frequencies, it has a very small radar cross-section. If you consider the cross-section of that, it would be pi a squared, where a would be the radius. It would be an order of magnitude, maybe 2 orders of magnitude less than this, when the wavelength is many diameters. Now as the frequency gets closer and closer to the the wavelength becomes about the same as diameter, then the radar cross-section approaches that of the real cross-section. And for high frequencies, when you're at very high frequencies, when you have many wavelengths that cover the dimension cross-section of the target, then that target appears that there's no real difference between the cross-sectional area you would see and the cross-sectional area the radar sees. This is important. So high frequency radars can discern things much easier than low frequency. One of the things some of you may realize is long ago, police radars were K-band, that's 10 gigahertz. Does anybody remember those days? Clap. All right, 10 gigahertz isn't bad, but two cars in different lanes coming at you, one speeding, one not. You can't differentiate the speeder. You can try. They went up to Ka band. Around Auburn, it's all K. In other parts of the country, they use KU. That's 33 gigahertz. That allows them to differentiate, and they can pick you out from the guy next to you. You follow me on this, class? And it's because, well, there's several effects, but one is the actual radar cross-section becomes very clear for the targets, and the approximate size is equal to the dimensions, cross-section dimensions of that car. All right, so that's the incident power density. Now, all this power hits this. This thing has some radar cross-section, and then the scattered power, we call this P scattered, is simply equal to the incident power density times sigma. Now the units of this are watts per meter squared. The units of this are watts. So now, once it hits and reflects, this looks like a transmitter. Y'all follow me? It itself looks like it's re-radiating the signal. And how much of the signal? This much. Y'all with me? Can y'all follow that? All right. So the signal comes, so much of the signal paints the, I use the word paint the card because it's common. It hits it, I multiply the power density by the radar cross-section, I find the amount of power reflected. Now that power will fall off as 1 over 4 pi r squared, just as if it was an isotropic radiator. There is some directionality, but it's included in the value of sigma. All right, so you don't ever worry about that. So now, the signal is reflected, it comes back and hits here. Next thing we get is the actual power density incident here, and this is going to be at the transmitter. So that power density is equal to the power scattered, it's P incident right there, times gain at transmitter over 4 pi r squared times sigma. Y'all see that's the actual power density it's going to be scattered. You with me on, I mean the total power scattered, correct class? Power density times sigma, that's the total amount of power in watts that's going to be re-radiated. Follow me? All that power falls off as 1 over 4 pi r squared. So now this is the power density back here from that reflection. And I might add, it's small. Very small. Y'all with me? All right? It should make sense the way I'm doing this. Now, yeah.
P incident's supposed to be P transmitter, right?
I'm sorry, P transmitter. Thank you so much. Yeah. So now that that power density is back here, I want to find the amount of transmitted power that's reflected and received. So now the next thing I want is the actual amount of power received by this radar. Can anybody think of what you do? I got a power density in watts per meter squared incident on this antenna. What do we have to multiply by to get the power received? The actual aperture, right? The size of the antenna, electrical size. So now we can say P received, and this is the important one, is equal to, start here, transmitted power, gain at transmitter, sigma, over 4 pi r squared. That's the amount of power reflected, right? Then I multiply that by 1 over 4 pi r squared. Now I have the power density that's incident on the receiving antenna. And how many remember what the formula is for the aperture of that antenna? Anyone? It's always proportional to gain, that's a clue. Go ahead.
Lambda squared over 4 pi,
Over 4 pi times
gain received.
gain of the receiver, right. Y'all with me? Now in monostatic radar, gain of the receiver and gain of the transmitter are the same. They are. They use the same antennas most of the time. There are exceptions. but they're rare. So, yeah.
For the, when the power bounces back off of the target, is it always assumed isotropic?
Well, here's the thing. No, it's not really, but that sigma is a function of the angle. So they include the effects of scattering from odd shapes in that cross section. But I don't want to get wrapped up in there and talk about take the isotropic and then weigh it by an effective gain of that. You don't have to worry about it. It's all rolled together, so sigma will be a function of angle. Remember, I'm trying to keep this at a simple level. This gets real complicated if you want it to get complicated, but if you follow along at the basics, the important stuff, all of it will make perfect sense, and it'll just seamlessly fall apart. Now, if you look at this, you see there's a lot of redundancy. We got 3 4 pi's in the denominator. We got 2r squareds, right? So I'm going to collapse everything, and I'm going to get a ratio of P received to P transmitted. Remember the Friis equation? It was power received to power transmitted. This is like Friis, only now we've got a target reflecting power. So now P received over P transmitted, right here, and that's important. This is going to be gain of transmitter, gain of receiver, and then it's going to be lambda squared over, or times sigma, radar cross section, divided by 4 pi cubed r to the 4th. And this is called the radar range equation. Now, this is a very basic but true statement. And you will see the radar range equation always be sort of is the starting point in most radar analysis. And here's why. You see this figure right here? We have an assumption of a distance, a maximum distance. That gives us the range. We know the smallest target, that would be a value of sigma that you expect to be able to resolve. Then you'll know the frequency, so you have lambda. With me on that, class? These gains are things you can adjust. But what usually amounts to is this ratio is something that's critical, and here's why. There will be noise power that you will be able to estimate in your amplifier system from the entire process. And you want that signal to noise ratio. The signal would be the power received. You want the signal to noise ratio to be above some threshold. So this magic number tells you what these gains must be. And I can't go into all the details, but just realize this is very important. So you could obviously estimate the received power from this equation if you knew the transmit power. By the same token, you could estimate the needed transmit power if you knew the receive power and these other things. In other words, if you know any of these values, you can get the other values. Do you follow me on that, class? Everybody follow me? So that's radar in a nutshell. I don't think you've seen this before in your physics courses. If you have, I'm surprised. But this is basic radar, and that's power received over power transmit. That's one aspect of radar. Another aspect is being able to determine the speed of something. And that's called the Doppler effect, or Doppler frequency. You've heard of this in physics, I'm sure. All right, that's the next. That right there, just write it down, and I'll give you some problems. But you can obviously see, if we have dipole antennas, right? Say they're halfway dipole. Those would be 1.64. With me? You got the frequency, you got lambda. You can figure, if I give you a target size at a given range, you can figure this ratio out. If I give you the amount of transmitted power, you can figure out the received power. You follow me? So it's more or less, it's something that makes sense, but you should know how to get the power density here, total reflected power, power density here, and total received power, all as separate things, all right? Just make sure you know how to do that. And if you've been studying along and know Friis, then this should make sense. Now the next thing we're going to do is the Doppler frequency. Is there any question about this before I continue? It's not hard, but it does require you to be attentive to detail. So the next thing is Doppler. And Doppler is Well, there's two types of ways of dealing with Doppler frequency. One is in the relativistic sense that if the target velocity as they're approaching the speed of light, then what we have to do is we have to adapt to the speed of light being a constant in all reference frames, and there'll be an effective length contraction. You haven't had modern physics, so you don't, but 99.999% of everything you do in the terrestrial environment we live in is going to be non-Doppler. The velocity of anything is much less than the speed of light. The only time that I know of where you have to worry about the Doppler effects with radar to calculate velocity is if you're dealing with astrophysics. And you're talking about supernovas and things like this, where you get an acceleration near like a black hole that approaches, where the velocities approach the speed of light of orbiting planets. But that is not something that we worry about here. Let's be honest. So what I'm going to do is just do Dopplers the standard way. And really, it's off in terms of Doppler shift. So here's what Doppler is. I'm going to use the same transmitting. This is going to be the gain of the transmitter will be equal to gain of the receiver. All right. Here comes my power transmitted. I've got a certain range out to the target. And now the target is a given size, but there's going to be a component, this thing's going to have a component of velocity along this axis. Do y'all follow me on this, class? So this thing's moving, and I don't care what its velocity is perpendicular, but there's a component of that velocity right in the direction of the target. Y'all with me? So like if the thing was moving this way, I wouldn't care about the actual velocity, I would care about the component of velocity along this direction. Y'all with me? Everybody? That's the thing that's important. So here's how we usually do Doppler. The first thing we do is we figure out the total distance the signal travels, okay? That total distance is 2r. Y'all give me that? It goes out, it hits, and it comes back. I'm not doing relativistic things, so there is no length contraction or anything like that. All right? The signal moves so fast it hits, and the target really doesn't move any appreciable distance before it comes back. All right? Now, first thing we do is find out how many wavelengths actually are in this path. In other words, if we're talking about the phase of the signal, each one of those wavelengths would represent 360 degrees or 2 pi phase. Do y'all follow me on that, class? Just freeze time. That's how many wavelengths would be from here to here. Agreed? Now, each one of those wavelengths, this is the number of wavelengths that are actually involved in this round trip. When we multiply these by 2 pi, now I get the total phase that the actual signal would change from the time it's transmitted to the time it hits and reflects back. Does this make sense to everybody? Right? First we find the number of wavelengths, then we multiply by 2 pi, right? Now that's the phase in radians. That's the total amount in terms of radians of phase shift that would occur from the signal leaving the transmitter and coming back. Y'all agree with that, class? Now, if I take a derivative of this with respect to time, then I get 4 pi divided by lambda times dr dt. Y'all agree with that? With me? This is non-relativistic. Now when I do that, so what is d phi dt? What do we usually call that? Radians per second is omega, right? Y'all remember that? Sure, it's omega. This is omega. That's a radian frequency, and you call it omega Doppler. And omega Doppler is actually 2 pi times F Doppler. Remember, omega is 2 pi F. Do y'all agree with that, class? This is not, I'm not trying to keep you in any way confusing. I'm trying to be as clear as possible. So let's just do this. One other thing, what is dRdt? And back in the day in physics, whenever you saw dx/dt or dRdt, what did you think of? Velocity. That's the velocity of this object, target, in the direction of the radar. It's the component of velocity in the direction of the radar. So now we can say this is 4 pi over lambda times the velocity of the target in the radial direction, and that's equal to 2 pi times the Doppler shift. And you can see what I'm going to do is cancel those 2 pi's, right? And so now I get the Doppler shift, and this is the one, the actual Doppler frequency shift, and this is a shift, is equal to 2 VR over lambda. And lambda is C over the actual carrier frequency. Now, it's important to understand in radar work, you're going to have something called a baseband frequency that has to do with a square wave pulse. The square wave, because listen, remember, if you have a transmitter, you can't transmit and listen at the same time. Does that make sense? Everybody should understand that. All right, so what you do is transmit. All right, when you transmit a signal, then you go dead for a while. You go dead until the furthest possible target's return is back. Then you send another pulse. That's the essence of radar. All right, you send, you listen, send again, listen. It's like you're listening for echoes. You follow me on this, class? If you send too quick, then you don't know which transmission the echo came from. So there's something called a maximum unambiguous range. These are things that I'm going to get into slightly to let you know how this is calculated. But for the most part with radar, basic radar, you transmit and you listen, transmit and listen, transmit and listen. And think of just, you know, echolocation in the most basic sense. I don't think we have anything around here. Have you ever been out in an area where there's canyons? Anybody? When you yell, you can tell by the time delay how far that echo came from. You with me? And that's basically with radar what it does as far as the distance. And I didn't mention that. I wanted to get to Doppler first. Now that Doppler shift, here's the thing. If you're approaching a target, the Doppler shift is going to be caused the center frequency. And here's really what happens. If you looked, and you don't have to write this down, but if you looked in the spectral domain and you look at the magnitude of the power received, and this is going to be in a frequency domain versus F, you're going to see at the transmit frequency, you're going to get something like this. There's going to be very, very little width there. You all with me on this? I'm just trying to show you. This would be the power density in the received signal. There would be something where you have a spectrum analyzer catching the signal and putting it up there. When you get a Doppler shift, if the thing's coming at you, this Doppler frequency will be added to this. And it will be actually F naught plus F Doppler, and it will be this way. And then, the distance from here to here, all right, is measurable and observable. Do you all follow me? Now, once you know that, look, once you know the Doppler frequency, you can get the velocity by multiplying by wavelength and divide by 2. Do you all follow me in this class? And that's exactly how police radars work. I mean, the standard handheld police radars, the police officer has to be pretty much aligned with the roadway. If he's at like a 80-degree angle and shooting you, he's not getting velocity. And there's no way for him to adjust it. I got a story about a police radar too. It has to do with my dog. Anyway, there are ranging radars. Ranging radars are different. These are sophisticated. What they do is find the location of a target, And then sometime later, milliseconds later, they find a new location. And they take a look at the actual delta R over delta T. They get the real velocity. They're expensive. You don't find these things on anything but military or in like commercial aircraft. Probably only at commercial aircraft towers and stuff like this where they're landing planes. You won't see this. This is expensive for starters. So here's my story about radar, Doppler radar. Now this idea works perfect. And I said, it's the velocity, the component of velocity and direction of target. But here's the thing with radar that I learned myself. I have a Greyhound. When we first got the Greyhound, there's a festival called Greystock out in Georgia. And they have a deputy sheriff come out with a radar gun. And they have a lure that the dog chases, and they'll measure how fast your dog will run. And our dog ran 41 miles an hour. Because I was somebody involved in it, I said, do you mind if I watch this? He goes, no, sure. And then he basically watched this. And he took it, now remember, this radar gun puts a very small dot at the ranges we were on the target. He took it, and he went right on the ground, 69 miles an hour. There was no animal. He just took this, because the dot itself on the ground, with respect to him, the component of that dot, its velocity, was moving that fast towards it. So you can take a radar gun, and just because that's the measurement on it, doesn't mean that's the speed anything's going. Because you understand how the ground can do that. You with me on that, class? The ground looks like, that spot looks like it's moving at you, and it's not. So just be aware of that when it comes to any kind of stuff that you do with real aircraft. And I've got other stories I can't tell you that have to do with this type of effect with landing planes and Doppler radar for targets if the target is below the actual altitude that the tracking plane is going. Because then if that guy gets near the ground, all of a sudden his radar's painting the ground and he's getting a velocity reading that is completely bogus. I'm just telling you there's all sorts of things that happen. But that's Doppler velocity, or Doppler shift, the frequency shift, and a couple of problems that can happen when you're doing that. Now the next thing I'm going to talk about is the total time delay. Most of you can figure out, if we took a look at this, just write this down, you'll see. This is how you get the range. If this is an actual time signature of the P received, all right? And transmit times here. This is going to be transmit time. All right, right here. That'll be at 0. And all of a sudden, T here would be the round trip time. I'll call it TR. So I'd see something like this. You with me? This is really what'll happen. You'll take a time record, and you'll see you send a signal, and you get something reflected back, just like you'd hear an echo. And you know the time delay from the time you made a sound to the time you hear the return. So how far away is it? Well, you know the signal traveled to R, where R would be the range to the target. Do you agree with that? And that has to be equal to the velocity of light times the actual TR, right? The time delay. Do y'all agree with that? If the signal's moving at the speed of light, then C times the time is the distance traveled, right? But with radar, it goes out, hits, and comes back. So it moves twice the actual distance to the target. You with me, class? And that means that the range to the target can be found by simply taking C times the time delay, or TR, divided by 2. And it's really that simple. That's how it's done, too. That's it. Now, there are some things you have to at least be aware of. Is anybody involved in radar in here? In any of your co-op or anything like that? One person? Well, there's a thing when you're dealing with ground-based radars at low observable ranges. It's called ground bounce. If I have a target out there and I got a radar here, The gain of most antennas isn't a pinpoint spotlight gain. It doesn't cause all the signal. So you'll get some of the signal hit the ground, hit, and reflect back. And you'll get, in the real world, you'll get something like this. You'll get that, then you get this, and you might get a fourth one where you get two, hits the target, then it bounces back in the ground. Now the first peak here has to be the direct range, right? Because it's the shortest possible time. That will give you the actual range, or the time delay to the target. But this kind of stuff can happen. Y'all follow me on that? It's really bad when you've got any kind of canyons and stuff like that, where you got a lot of ridges and things. You can get a lot of problems with ground bounce. But that's sort of a thing. Just be in the back of your mind if you're working with radar. Remember, this stuff that I'm showing you is in the purest form. It's not involving all the complexities that happen in the real world. Just be aware of that. Okay, so now we've covered range to target, power density received from a target, and Doppler shift with radars. I can tell you there are two other things that are usually talked about that aren't in his book. One is the maximum unambiguous range. It's how far out a target can be, or what's the maximum possible range we can see a target and know it's actually at that range without being ambiguous. And you understand, remember I said the problem of sending one pulse and a second pulse before the first echo is received? You don't know which one? So there's a thing called the maximum unambiguous range, and then there's a thing called range resolution. So in terms of the range distance, what's the smallest target you can resolve? Why that's important is when you have aircraft approaching you. Now, I know this is the normal way you think. Well, if all the aircraft are in a line, then the first one simply eclipses all the other ones. You never know. Well, aircraft don't exactly fly in a perfect line. They're staggered, but they are in the same corridor, you might say. So what's the minimum distance needed between aircraft before you can differentiate two? That's range resolution. It's the same thing with automobiles when cars are driving. Range resolution is important. I'm going to go through these. And for me to do this justice, I have to show you the timing diagram of a common radar signal. So the transmitted power from a typical radar looks like this. If this is time and this is power transmitted, it will look like this. This is periodic, and it just goes on and on. This has some level, and you can just call that PM for max, or P max here. And it has a given duration, tau. And the period is capital T. It's actually called a pulse repetition interval. They're interchangeable terms. You're used to T for period, aren't you, class? The PRI is a common thing in the literature and in discussions. It's the pulse repetition interval. It's the time it takes before the next pulse. And this is periodic. So let me take you through it. We transmit, then we listen. We transmit, then we listen. You all with me, class? Now, there's more to this, but in a nutshell, when we take a look at the maximum distance that we can discern unambiguously, the way we get it is this. Well, this is my radar here, and here's the target. And this is we're gonna call this the maximum unambiguous range. Well, I know the signal goes out and comes back, so it's 2 times RU would be the distance. Agreed, class? Now, when I say this is equal to C, the speed of light, times T, this value of T has got to be this value of T. And here's why. Because now, send the signal out, right? It hits, it has to come back before I send the next one. Do you follow me on this, everyone? So I can say the maximum unambiguous range is equal to C times T over 2, or, and this is called maximum unambiguous range, and that's C times, a lot of times it's PRI or T divided by 2. Sometimes you see it stated as C over 2 times the PRF. That's the pulse repetition frequency. It's just 1 over the PRI. Trying to get you at least a little bit familiar with terminologies that you'll encounter in the real world. Pulse repetition interval, pulse repetition frequency are used most of the time. They don't use period T, even though I like period T because most of the time you're familiar with that. And that's, y'all with me, class? I'll put this up on one up. Now, that's how you get the maximum unambiguous range. It's a very basic, like way I'm showing you. There's so much more to this. The actual duty cycle, which you're familiar with, I think they call it duty time, is just tau over T, or tau over the PRI, or tau times the PRF. And that's duty cycle can have a maximum value of 1, which is insane because then you can't listen. And it can have, typically it's of the order of 0.1. It's about 10%, 10 to 20%. They get, sometimes they get up to 50% duty cycles for different reasons. But usually you get about 10%, 10 to 20% on time. That's it. For most radars. And I say that and I'm always thinking to myself, well, I'm not real familiar with some radars that are used these days in small planes and stuff. But the radars I'm familiar with, that's true. Now, the next thing is range resolution. And this is the last topic we're going to cover. Does that make sense to everybody? These things should make sense, all of them. There's nothing here that's really some wild physics. Doppler shift should make sense. Maximum unambiguous range. This is the range resolution. And the nice thing about this, if you know this formula, range resolution is no problem. So what is range resolution? Don't write this down, just listen. So I send out a signal, and I have a target of some length L. Y'all follow me? I'm giving you the dimensions, radial dimensions. All right, this signal goes out, hits, comes back. So the actual, the shortest round trip would be, and I'll call this to the front end right there, just R. The shortest round trip would be 2R. You with me? Now, maybe I shouldn't have done L here. I should have put 2 targets here. Now for the second target, which you don't realize yet, when you have an edge like that, it's a reflective point. And when the edge disappears, it's a reflective point. So if you have a very long object that's conducting, and you send a pulse and hit that thing, you'll get a huge reflection off the very front, and you'll get a reflection off the very back. Even though your eyesight doesn't see the very back, the radar signal will. It'll reflect off. So this is, look, there's 2 points of scattering right there. This is the shortest distance. The longest distance would be 2R plus 2L. Follow me? Now, if we think about the length of time here, 2R right there divided by C would be T1. This would be the shortest time, right? And then 2R plus 2L over C would be the longest time, right? Y'all agree with this? If I subtract those two, I can see that the delta T would be equal to 2L over C. And what this actually turns out to be is 2 delta R, because that's this right here. The L really is a change in range to tell me what I can resolve. And that means this, that this delta T is associated with this value tau right here. And therefore, delta R, just write this down, range resolution is equal to C tau over 2. And if you look at that compared to this, they're the exact same form, only instead of T, it's tau. Now you can do the math on, you can go through the math on this one, but you'll find that the minute the on time is longer than this value, the signal reflected from here will still be present when this one starts coming back. And you can't tell which signal is reflected from what point. All right, so that's how that delta T enters in terms of being able to differentiate different reflective points. And I don't expect you to be experts on this, just have an understanding. I will give you problems that are representative of anything you need to know for homework, all right? Now, on Wednesday's class, I'm going to do some array theory, but I'm not going to put it on the exam. I'm going to just go through it, and then I'll take questions and sort of do a wrap-up for the exam on Friday, okay? Please come. If you have additional questions, I'm in my office after, so if you need to see me, just send me an email.